Here is Maria Tavares. I work. So I am Maria Tavares. I work at the Federal University of Rio de Janeiro in Brazil, and it's my great pleasure to chair this session that honors Omer Schramm, extraordinary mathematician whose life was tragically cut in 2008. So it's probably not needed for almost everyone in this audience, but let me just remember Schramm's work had and still has a tremendously deep impact in probability, especially, but not only for the conception and development of the SLE evolution, which now stands for Schramm-Loebner evolution, and which completely transformed the mathematical understanding of planar processes arising from statistical physics. With this spirit, it's a big privilege to introduce Professor Omer Angel from the University of British Columbia as the 2020, we are 1 year later due to the pandemics, Schramm's lecture. Professor Angel is the leading scholar whose research interests are mostly centered in probability and discrete mathematics, include random graphs, percolation, random maps, and scaling limits. So a lot of common ground with Schramm's interests, with whom he indeed co-authored 2 papers, at least 2 that I know of. So today, Professor Angel will talk about balloons in space. It's a big pleasure to receive him. Omer, please, the room is yours.
Thank you very much for the introduction, Eulalia, and for the organization, also to Siva. And it's, well, it's really an honor to give this lecture in this forum. It's very unfortunate that I couldn't make it to an in-person meeting in Korea. I was rather looking forward to that, but we take what we can get. And so this is what we can get this year. And so, yes, I will indeed be talking about some recent work with Gura Bray and Inon Spinka of Victoria, and currently of UBC as well, but soon to be at the University of Tel Aviv, about what we call a balloon process. So the title is Balloons in Space. But as we will see, this actually ties into some work of Oded as well. So let me just dive right in. And the process that we are considering is the following somewhat natural process, and this is our model. So we are given some metric space, so let's call it X. D is a metric space. And mostly the natural candidates are either the Euclidean space or hyperbolic space, but you can also consider various graphs like ZD or trees, and a lot of what we do applies in fairly general metric spaces. And you start with some point process. So, so let's say pi is a point process in X. And you can think of it as a Poisson process. That's the most natural example, but of course, you can ask for any other. So the key example is the Poisson process in, let's say, RD. So that's something you can keep in mind. And now what we do is the following. So at every point of this process, you start. Let's imagine that at every point of this process, you start growing a balloon. And these balloons grow at rate 1. So at some small time, you get something like that. And they all grow at the same rate for us. So at some point, what might happen as they grow is that they touch each other. So suppose they've grown a bit more. And now those 2 balloons here are touching each other. So when 2 balloons touch, they annihilate. So let's delete them. Well, let's not delete them, but they annihilate. So I'll just put it down. So so from from each point x of pi of the point process, we grow a ball at rate 1, and when two touch, they annihilate. And this started with a question that was posed by my other advisor, Itai Benjamini, and he asked, is this process recurrent in the sense that every point will be covered by balloons infinitely often, or is the process transient in the sense that eventually points will be uncovered? And I will tell you some answers about this, but maybe first we can start with a simulation. So it's relatively straightforward to encode this and run. So what we see here is, okay, so let me stop it right away. So you start with a Poisson process. This is in a segment of the Euclidean space, and actually the simulation extends beyond the image, but you only see what's in the image. And you see the balls are starting to grow, and if you have sharp eyes, you'll see that some of them are in gray. So when two balls touch and stop growing, then we freeze them, but we show them in light gray. So the process looks something like that. And there's a surprise at the end of the movie, so you should stay until the end. And so there is also a surprise in the middle of the movie. And now we have a time 1, so you can see there's quite a lot of balloons that have already started growing, already vanished, but some balloons still remain, and these are those balloons. Now, if I just kept the simulation going, then eventually the balloons will be too big to see in the screen. So you'll either see just part of one balloon or nothing. That's not very interesting. So something that you can do, you can just start zooming out. And you can start zooming out so that the balls have a constant radius, and now I'm no longer showing the ones that are disappeared. So you can think of this as the same simulation that keeps going on, except that now I'm zooming out, so we see new balloons that were previously too far to see, and they come in. So we zoom out so that the balloons always have the same apparent radius. So this is the model that we were studying. And if there is any questions or comments, if anything is unclear, then please do interrupt me, and I will try to clarify. But we can also do the same thing in hyperbolic space. So again, in hyperbolic space, viewed as the Poincare disk, and the blue balls here all have the same radius in hyperbolic. So that's how hyperbolic metric goes. And you can see that they grow, and when two touch, they annihilate. And you can keep going. And sometimes it seems that you get some balloons that seem to come quite far towards the center, and it's a bit hard to determine if they are going to make it or they will touch some other balloon and annihilate before. But if you look at the picture at some relatively large time, as this simulation shows, so it appears that towards the end, all the balloons are quite far away from the origin and and are no longer seen. So, and I see a question in the chat about the motivation for this model and application. So this model, it turns out, is connected to several things that were studied before, and I will come to some of the background in a few minutes. But the specific motivation for this also comes from the question of particle systems. And some questions, if you have, for example, if you have annihilating random walks, so instead of having a ball grow, you just have random walking particles, and whenever two touch, they annihilate. So there are questions, under what conditions is this process recurrent? So you start with some infinite graph with a particle at every vertex, and you want to know, is this system recurrent or transient? So this is a similar family of ideas, and that's what gave rise to this model. And we don't have any concrete applications for what we did, but some of the tools we developed in the process, I think, may be of some independent interest. So we will see some of them again in a few minutes. But if there are any other questions, then please do interrupt me. But we've seen a simulation. And let me just state right away a theorem that, two theorems in fact. So one theorem is that in RD, this is recurrent. So balloons are recurrent. And the second theorem is that in the hyperbolic space, in the hyperbolic plane, they are transient. In the sense that eventually you don't see any balloons near the origin in hyperbolic plane, but in Euclidean space, every point is covered by balloons infinitely often. Now, this is closely connected. When one of the first things you realize when you start to think about this model, it's closely related to some work from a few years ago of Holroyd, Pimantel, Peres, and Schramm. And they studied various models of matchings. So in particular, they asked what happens if you take 2 points processes. You take, let's say you have the black points, and you have, you can consider black points, you can consider red points. So, so suppose we have 2 sets of matchings like that, and now you can consider a matching between them. So you want to associate to each blue point, to each black point, a red point. And there are many questions about what sort of properties such matchings may or may not have. So maybe you can do things like that. And maybe. And so it turns out that that if you consider the single color version, so if you have a single color stable, what is called as the stable matching, which I will define shortly. So this is related to the balloon process. So this gives the correspondence. So every balloon is matched to some other balloon with which it pops. So the single color stable matching gives the paired balloons. And so what is this stable matching? I will just define it. So stable matchings have a long history. They go back to the early 60s with the work of Gale and Shapley, who showed that under fairly general assumptions, stable matchings always exist. But the way you can construct these stable matchings, either with one color or with 2 colors, so the stable matching construction, so if you have a pair that are mutually closest, if some pair of points is mutually closest, then you pair them, you match them, and remove. So if you have a point X and the point Y, and there's no other point nearer to X than Y and no other point closer to Y than X, then you just match them and then you remove the 2 points and continue as if they were not there. So I will not go into the general theory of stable matchings. There's a lot to say about this, but you can show that this process is relatively well defined on fairly general point processes. So essentially, there's no infinite descending chain. So you have no infinite sequence of points where every point is closer to the previous one. So And the Poisson process, it's not hard to show, has this property. So you can, so there's a well-defined and unique stable matching. And there's a question. So in this paper of Peterson and Schramm, they studied the distribution of the distances to the matched points. And they asked, well, what can you say about the distance to, if you take a typical point, what can you say about the distribution of the distance to its matched partner? And in some cases, and there again, there are many settings. In some of them, this is known. In some settings, this is still partly open. But some of the work that they have done certainly is useful for us. And in particular, let me define this. So let Tx be the time at which a point is the balloon is matched. So this is the time a ball at a point X is matched. So it meets another ball and they annihilate. So one of the things that they have shown is that you have infinitely many points that are matched halfway to the origin. And this is a consequence of what they call an infinite appetite property. It's a consequence of the fact that every point is eventually matched to some other point in this process. Nothing is left unmatched. And in order to do this, they argue, well, if you add some point somewhere else, somewhere here, then it might grow large enough to be matched with the point near the origin. And in order for this to happen, they have to reach halfway. They have to grow to half the distance. So this is, so you'll note that Tx is half the distance to the partner, to the match of X. And so one of the things that they have shown, and let me state this as a theorem, which goes back to this paper of Holroyd, Pimentel, Peres, and Schramm. This says that almost surely, if you look at the lim sup of Tx divided by the norm of X, then this is at least 1/2. So you have infinitely many points that reach halfway, where the balloon reaches halfway to the origin. And while they do this in Euclidean space, which is what they were thinking about, the argument works for relatively general point processes on relatively general spaces. So in particular, it works on hyperbolic plane as well, and also on other spaces that we have considered. And not just for the Poisson process, but this does require some properties. It requires, in particular, insertion tolerance and some version of deletion tolerance, which the Poisson process has, but not every process does. So this is the process, and the theorems that I've stated above about recurrence and transience in the hyperbolic and Euclidean space come from the following. They are corollaries of the following theorem. So in the Euclidean space, we actually have that lim sup of Tx over X is infinity almost surely. Whereas in hyperbolic space, we have that the lim sup of Tx over X, where this is, you should think of the norm as the distance from the origin. This is at most log 2 over log of 1 plus root 5 over 2. And you'll note that this is greater than 1. And sorry, this is lim inf is greater than that. Yeah, sorry, it was lim sup again. Sorry about the confusion. So anyway, what does it mean that the lim sup is greater than 1? It means that only finitely many points reach to the origin, And in fact, there is some fraction where only finitely many points reach that fraction of the distance towards the origin. Whereas in the Euclidean space, Tx much larger than x means that the ball at x not just reaches the origin, so this happens if Tx is larger than the norm of x, but also it gets much larger than that before exploding, so that the origin can be relatively close even to the center of the balloon, infinitely often. So this is the way we get these results. Now my mouse is slightly frozen, but yes. So if there are any questions at this point before I say some things about proofs and then some other related things, then now would be a good time. And so let me introduce one of the tools that we have used to prove the Euclidean case. And this is something that has a very classical feeling. And when we found this lemma, we said, well, this is surely known. And we asked some people, and in fact, remarkably, Ofer Zaytouni almost immediately was able to give us a reference to a somewhat obscure paper from the 70s of David Tani, who was a student of Harry Keston. And this result, and Tani had this result in one dimension, but in higher dimensions, this, as far as we can tell, this has not appeared. So this is the following theorem. So let X be some ergodic process, or actually translation invariant is enough. Translation invariant real valued process in ZD, but it also works in Euclidean space so you can generalize this. But let's just state this in Euclidean space in ZD for simplicity. Then almost surely lim sup of xn over n is either 0 or infinity. So this seems very classical, but I'll show you a proof, and as far as I know, it's new. Now I see a question in the chat about hyperbolic spaces in higher dimension. And unfortunately, our argument in hyperbolic space is somewhat specific to 2 dimensions. And it would be very nice to see a proof in any dimension hyperbolic space, and as well as several other settings where arguments fail. But I will talk a bit later about the argument for hyperbolic space, and it will be clear why we are, in what way it is deficient. But thank you for the question. So, okay, so that's the theorem again. If anyone has a reference for this from 40 years ago or less, that would be lovely. But here's a proof. The proof is really nice, and I'd like to show you. So what does it mean that xn over n is large? So let's look at the process x. So we have some process which, and you think of this process as a process of trees. So at every point, at every integer point, we have a tree growing. And most of the trees are maybe very short, but some of them are quite tall. And xn over n is the angle at which a tree appears if you are standing at the origin. So suppose we are standing here at the origin. Let's say we are here. And we have a tree here that has a fairly large angle because it's relatively high and relatively close. So xn over n, so this is the angle a tree top is seen. So what does it mean that the lim sup of xn over n is, let's say, greater than 1? So xn over, so let's, okay, so we can consider an ergodic component separately. So we can assume that the process x is ergodic and prove it under an assumption of ergodicity. So let's say, without loss of generality, x is ergodic. And let's assume that xn over n is greater than 1 infinitely often, almost surely. So suppose the lim sup is at least 1. So the lim sup is a constant, since it's invariant, so it's an almost true constant. Suppose it's at least 1. So this means that we can draw at each point, actually let's do this here. So we can draw at each point a cone of angle 1. And what this tells us is that that 0 is almost surely covered by one of these cones. So if you have from every tree you put a cone with slope 1, then every point is covered by one of these cones. So almost surely the basis of cones with slope 1 is all of the space, is all of RD. So that's what we have. So let's draw now just the basis of the cones. And now this is no longer a one-dimensional picture. So we have the basis of the cones, which are some set of balls of various radii. And these balls cover all of space. And now we have the Vitali covering lemma. The Vitali covering lemma says that we can find a collection of disjoint balls. So let me paint them in yellow maybe. So this is a subset of these balls that are disjoint. So make them a disjoint subset of balls. Let's call them BI, such that if you look at all of space, this is equal to the union of 3 times BI. So if you increase each of these balls by a factor of 3 and take their union, so you take only the yellow balls, which are disjoint, but each one is blown up by a factor of 3, then this covers all of space. Or more generally, it covers everything that was covered by the previous balls. So that's the Vitali covering lemma. It's true in any metric space. The 3 should actually be, let's put here 5, but it's true with any constant number than 3. So we have such balls. And now let's ask what happens if we look at some taller cones. So suppose I look at cones with slope 2. So these are thinner cones. So the question is, do these thinner cones with slope 2 also cover everything? Because if they do, then I know that the lim sup is at least 2. So what is the slope of cone 2? So the slope of cone 2 gives me some smaller ball inside each of the, so I have this smaller ball inside each of the yellow balls. And it's half the size. So this means that there exists a set such that a set of disjoint half of BI, where the union of 5 BI covers all of space. But this means that this half BI have to cover a positive fraction of space, because if you increase a ball from half radius to 10 times the radius, to 5 times the radius, then you increase the volume by at most 10 to the d. So so what we get is that the set covered, so the union of half BI has density at least 10 to the minus d, because if you blow it up by a factor, by a factor of 10, it covers everything. And every ball is covered by 10 to the, increased by 10 to the minus d. So what does it tell us? We get that with probability at least 10 to the minus d, we have that xn is at least 2. So with probability at least 10 to the minus d, xn over n is at least 2 for some n. There exists some n such that xn over n is at least 2. But if you get this probability is at least some constant, then it's almost true because they offer by ergodicity. So, and there is a small step that I'm skipping here that you need to, you can say that you only look at balls that are larger than some threshold, then you can take this threshold arbitrarily large, and this will give you infinitely many such points. So ergodicity, we get that almost surely there exists such an n, such that xn over n is at least 2. And that means that what we have proved is that if the lim sup, so we have shown that if the lim sup of xn over n is at least 1, this implies that the lim sup is at least 2. And there's nothing special about 1 and 2, so this proves that if it's not 0, then it has to be infinite. So that's a classical new result, or a new classical result. And this actually proves the main theorem that I stated for the Euclidean case, because in combination with the Holroyd's Pimentel Perez Schramm, that we know that the times at which balloons pop is at least a half. This gives us that the times at which, so we know that the lim sup is infinite, and this tells us that there exist balls where the time that balls that only meet another ball at a time much larger than the distance from the origin, so they will cover the origin at some point. So that's the first part of the talk. And the second part will involve trees and hyperbolic spaces. But before I go into that, would be a good time for questions or request for clarification. Or so this we have seen. Okay, so if there are no questions at this point, then I will continue. And so, so the next step is to ask what happens in hyperbolic space. How do we see that it is different? And in fact, for hyperbolic space, we go and look at processes on trees as a warm-up. Sorry, my mouse is frozen again. Yes. So let's consider trees for a minute. So let's consider TD, which is the d-regular d-array tree. So T3 is the 3 regular infinite tree. And you can consider a similar process also on trees. And so actually maybe, sorry, before I go into trees and this, let me state a few more questions that are relevant and for a Euclidean space and come out of this. And this would be a good time to discuss them. So let's say that pi t is the process of points that are still alive at time t. Live centers at time t. So what do we know about this process? So the easiest thing that we can say is that these points are well separated, because each of these points has a ball of radius t around it that cannot be and those balls are disjoint, otherwise they would have popped. So by disjoint balls, from disjointness, we know that pi t must be 2t separated, meaning that the minimal distance between points of pi t is at least 2t. And the consequence of this is that the density of pi t is at most 1 over the volume of the ball of radius 2t inverse. So, which is on the order of t to the minus d in Euclidean space. And there is a question, is this actually sharp? So this is a conjecture, and this conjecture in some form, you can see it also in the paper of Holroyd, Peterson, Schramm. This is a question about the tail of xt. So this gives us an upper bound on the probability that xt, the distance to the match, is larger than t. And is there a matching lower bound? So the conjecture is that this is sharp. That is that the density of the process pi t is actually asymptotic to some constant t to the minus d for some constant. And there's an even stronger conjecture that you can make, which is that this process has a scaling limit. So a second conjecture is that if you look at, if you rescale this process by a factor of t, so this is the times the zoom out that we've seen in the animation earlier, where we keep the balls at a constant apparent radius. So this converges in distribution to some process, I don't know, let's call it gamma. So there is some limit process. So this is a conjecture. In one dimension, this is actually known. There is some work in progress by Ander Holroyd, Tom Liggett, and there was one other person involved whose name I forgot. I think he was a student, but yeah, unfortunately, since Tom passed away and the third person less active, this process, this is somewhat slow to be written, but in one dimension, and in any case, this is relatively well understood. So, but the conjecture is that such a process exists, and moreover, I would conjecture that if you start with fairly general point processes, and you start applying this process in rescale, then you would converge to this, you'll always converge to this process gamma, regardless of what starting point you take. So that's all I will say about Euclidean space, though. And now I really will move for the last 15 minutes or so to hyperbolic space, and I will start with these, which are a toy model for hyperbolic spaces. So let's start with a tree. So as I was saying before, so TD, so this is the DR irregular tree. And suppose you want to consider a point process in TD. So let's consider the process pi t in TD. So what does it mean to do this whole thing on the tree? So you can consider the tree also as a metric space. And if you want this to be a continuous metric space, you can just think of edge lengths of edge 1. So these are just segments of length 1. And on these segments, you can have points. So the points will be, you can have multiple points initially on one segment, and some segments may be empty. So these are the centers of the balloons. And you start growing the balloons around these points. So initially, each balloon is just an interval, but once it reaches one of the branch points, it starts being more complex. And again, when two meet, so the whole process is exactly the same. This is just a continuous metric space made out of segments glued at the endpoints. So let's consider the set pi t. So pi t is a well-separated set again. So pi t is again 2t separated. So there's a question, how big can a 2t separated set inside the tree be? And the easiest case, and suppose you just take vertices. So let's consider more specifically. let's consider pi t hat. So these are just the vertices nearest to the points of pi t. So if you have so every point that is in pi t, I just move it to the nearest vertex. So what's the probability that a vertex is contained in this pi t hat? So if you have so this is a 2t minus 1 separated set on the vertices of the tree. And there is a question, so how dense can such a set be? And the trivial bound is the volume. So the trivial bound that we had already before, we said, so trivial bound, we said that the probability that, let's say, the root of the tree is contained in pi t hat is at most 1 over the volume of the ball of radius 2t minus 1, or well, you get a ball of radius t. Let's not worry about constants. So the ball of radius t. And this is not going to be enough for a result. We need something better. And fortunately, we can do something better because this is not just an arbitrary process. So the first case where something like this was done is in the work of Bolobash, where he looked at independence ratios. So there's a question, what is the largest independent set? So independent, no two adjacent nearby vertices. And so Bolobash, and this was in the early 80s, I think 81, I think. So bounds on the size of independent sets in various graphs, in some regular graphs. And on the tree, the trivial thing you can do, you can say, well, the tree is bipartite. So you can color the vertices black and white and take all the black vertices or all the white, half with probability half. And every point is contained in this independent set with probability half. But fortunately, or fortunately for us at least, the set pi t has some additional properties. So pi t is actually a factor of IAD. And if you give but what it means is that you have some IAD randomness initially, and pi t is this process is determined from this randomness in a measurable way. So whether you have a point at near the origin at time t is determined by looking up to some just by running the process. So initially you have some IAD randomness in the locations of the points and the number of location and location of the points on the edges, and pi t is determined by. And for you can get a better bound. So Bolobash. And the idea basically goes back to the idea of Bolobash. So the idea is that you can approximate TD by a uniform d-regular graph, which you can sample, for example, using the configuration model. So take n vertices and put d random matrix between them, or d half edges, and match them in pairs. And in this d-regular graph, in a finite d-regular graph, you can actually estimate, and this is essentially the birthday effect, that if you want to have, that it's extremely unlikely that you'll find a set of balls, a set of points in the graph that are well separated more than a ball of twice the radius. So this gives the following lemma, which I will leave the details out, but so there is a lemma that the probability that the root or any vertex is contained in pi t hat is at most up to constants. Well, you get the ball of twice the radius, basically. So the balls grow exponentially. So if you want the balls to cover square root of the volume, then you need the ball of radius t to cover you need the ball of radius t to cover half the radius. And what we get is something up to constants. Let's not write the constants, t over the volume of the ball of radius 2t. So essentially you get double that. And what this means, this now you can just use Borel-Cantelli. So Borel-Cantelli implies that almost surely, if you do this on, if you run this balloon process on the d-regular tree, then the lim sup of the time at which x pops divided by the norm of x, the distance to the origin, is at most 2. So that means that points only reach halfway, so it's at most a half. So points only reach halfway to the origin. Now, in order to carry this over to hyperbolic space, to the hyperbolic plane, we just say, well, the hyperbolic plane is very similar to the tree in many ways. So let me just find this picture here. Yes, so this is a picture of what you can do. So you can consider the hyperbolic space, and you can triangulate it. So the blue edges partition the hyperbolic space into a triangulation. And the black is the dual graph. So you have a black vertex at the center of each blue triangle, and then this gives the 3 regular tree. And now you can say, well, if you have a point in one of those triangles, let's just map it to the corresponding vertex of the tree. So when you map a point, in the tree, then you get some process on the tree. And this process is, if you have points in hyperbolic space that are well separated, then you want to say, well, also the points in the tree are well separated. And this is not completely right because you have these corners of the triangles where they get very thin. So you have to be a bit careful, and you need to truncate some points, and there's some extra arguments there that I will not get into. But for the hyperbolic space H2, let me say, we approximate H2 is approximately the 3 regular tree, and apply the result from the tree. And this is why we get, there's a distortion in this embedding, which has this log of 1 plus root 5 over 2. And this distortion is the reason that we don't get the full bound. So the conjecture, so let me just state a conjecture about what happens in hyperbolic space. So, and the conjecture is that in hyperbolic space, in any dimension really, the balls only go halfway towards the origin. So we have that the lim sup of the time at which a balloon at x vanishes divided by the norm of x is equal to a half. And I should say this is also equal here. So Borel-Cantelli gives the upper bound, but the lower bound is from the previous arguments that we had. So we say that the lim sup is actually equal to a half.
Sorry, can you
Yes.
maybe move the picture, because one cannot see what you are writing?
Ah, sorry, I will remove the picture. It's such a nice picture though. Thank you. Yeah, so we have so this is the conjecture that in hyperbolic space this is actually equal to a half. So the balls only get halfway towards the origin, and I will just mention that There is some possible approach towards doing this that it would be very interesting if someone could make this work. And this goes back to some notions of random negatively curved spaces. So so there is an object called the Weil-Peterson measure. And this is a measure on manifolds of a given genus, also possibly with some fixed number of marked points. And this has been studied quite a lot. So there are some landmark works of Mirzakhani, which estimated the total measure. So the total volume of the space of such manifolds, of the space of surfaces, and some aspects about their geometry. But something that we would like to argue is that there is a similar birthday phenomenon here, that it is impossible to find a large number of well-separated points. So the conjecture, so there are some theorems of Mirzakhani that I will not quote, but the conjecture is that most spaces, so this is, let's call it VG, so the space of genus G. So most surfaces in this VG with respect to the Weil-Peterson measure, if you look at the largest number, so the maximal density of let's say R separated points is approximately 1 over the volume of the ball of radius twice R. And you might need some extra log factors, but essentially this is something like a birthday effect in random geometry. So if you have a random geometry for the spaces, then if you take any set of points, the probability that the balls of radius R around them will be disjoint should decay extremely fast once the balls cover much more than the square root of the volume. And these are hyperbolic spaces, so balls of radius R have the square root of the ball of radius 2R. So that's roughly where this comes from. And these arguments based on the configuration model. So the configuration model does this for us on d-regular graphs. And that's why we're able to get very precise results on trees, which are the limits of d-regular graphs. We do not have such a good understanding of hyperbolic spaces, so this is still open. And as Didong asked earlier, this is also open. So even the transients result is open in hyperbolic space of higher dimension, since the distortion when you embed trees becomes too large. So it's no longer sufficient for the transient. Yeah, so I think this is a good time and a good place to stop. I will maybe mention one more quick comment, that there is also a lot of questions you can ask. What happens if the balls do not all grow at the same rate? And while some of the things go through, some of the things fail, but I will stop here and we can discuss this in question time if people are interested. So yeah, so thank you for coming and thanks for your attention.
Thank you very much. Thank you. So there is time for some questions, if someone can make by writing in the chat or by maybe, I'm not so sure everyone can unmute, but there is one question.
There is a question in the chat.
Yeah.
If you pop the balloons only after hitting K other balloons. So, right. So this is indeed an interesting question and very interesting. So there are some works related to the matching in the matching literature about what happens if you want to match not pairs of points, but if you want to, for example, split points into triplets. You can do this both if you have a single color or if you have multiple colors, and there are many possible generalizations. And for some of this, so we haven't tried going through the arguments in detail. For some of these things, I think things will go through, but it is quite delicate. So in particular, if you say that a balloon pops after hitting k other balloons, regardless of whether these other balloons meet each other or not, then you get some a potentially complex graph on the tangency, on the interaction between balloons, and so yeah, so I don't have an answer for this specific version right away, but yeah, but it's a nice question. So
any other question? Yeah, there is also a situation like the balloons stop growing when they touch each other, but they don't disappear.
Yes, I think there are some papers about this, where it's called the lily pond model, where you have, you think of lilies growing, and when two of them touch, they stop growing. And there are all sorts of questions about the set that is covered by them and the leftover set. I don't think there is any significant results about this, but you can ask this. So one of the things that we're looking at is what happens if some of the balls don't grow at all. So I see there's a typo here also. So some of the balloons grow at 0 rate, and some grow at a positive at rate 1. So you can think of them as balloons and pins. So you have two balloons, so two balloons can touch and annihilate, but also if a balloon touches a pin, then the balloon and the pin annihilate. The pin is also removed. And in this case, there is a question, do any pins remain in the process? So you cannot have any balloons remain, because if you have some density of remaining balloons, then they will eventually pop. But if you have, if you start with more pins than balloons, then certainly some pins will remain. But suppose you start with 1% pins and 99% balloons. So, are any pins going to survive in this process?
Yeah, that's it. So I think we are about the time to close, unless there is some other question. If not, we thank Professor Omer Angel again, and we will resume.
Yeah, thank you again for the invitation.
Thank you.
And hopefully we can see each other in person at some,
yes, hopefully
in the near future.
In the near future. So let's see. Let's hope for the next year at least. Yeah. Have all the best wishes to.
Thank you. So I think Percy is the next speaker, but you said there is a different link for the.
Yeah, I think we need to go to another link.
Yes.
Yeah, but the question that I have is when those that don't grow, they are the ones that freeze the rest, and that is not clear if the process is well defined at all. I don't know if
so you're saying, suppose the pins
like that. I have green points and red points. The green points grow at rate 1. When they touch a point, everything gets frozen and gets red. When someone else green touches red cluster, gets frozen and gets red.
I see.
It's not clear that this process is well defined at all. For at least, I mean, if the density of red initially is big, then you can make a block argument. But if you have very little density, then it's not so clear if it's well defined. I don't know, at least for me it's not.
Well, but so if when things touch the red point, they become red, then
And
the
stop
density will, yes, then the density will become large very quickly, I should think.
Yeah, yes, but the question is,
But
it's
yes,
well defined in the sense that you converge to something. That this
yes,
process,
yeah,
it's not so
yeah,
clear.
it's not obvious. I agree.
Yeah, but now some of the ideas that you presented gave some sort of hope that one can treat.
Yes,
A lot of
yes,
that
that's
I couldn't do with Yuval including.
yes, yes. So there are several variations of this that we would like to understand, and
the poison.
I
It's
think
like the red is the fire in the forest.
yes,
It gets burned, and then another thing keeps going, and then gets burned again. And so
yeah,
how
it is
can
a
you,
bit reminiscent.
yeah, of that, yeah. So thanks a lot, and best wishes to you. And,
You're welcome. Yeah, thanks for hosting.
thank
And,
you. Now we go to Percy's
yeah,
lecture.
yes, I would also like to go to his lecture. But thanks everyone.
Bye.
Bye.